Hey, good morning, class. How are things going today? All right. What I'd like you to do is take out the notes, the lecture notes that I had you copy down from yesterday. Okay. I'm going to go over the first 2 pages of those notes with you in this first video. And then the second video, I'm going to go over page 3 of those notes. Okay. So the first page lists 5 characteristics of a series circuit. And then the second page, I build an example problem. And then the third page is a sample test question, is what that looks like. I'm not sure if we're going to be testing that way on this online environment, but if we're in person, that's what that would look like. So first of all, series circuit. What is a series circuit? Well, the number one thing that characterizes a series circuit from any other is it only has one path for current to flow through. Only one possible path. So when you draw a picture of a series circuit on this second page now, you're going to be flipping back from page to page. This box that you see here is a series circuit. Okay? These squiggly lines are schematic symbols. This drawing is called a schematic diagram. The squiggly lines are called resistors. And this little symbol down here with a short line, long line, that's the battery or power supply or your voltage source. Okay? So as you can see, there's only one possible path for the current to flow. It has to go from this, direction here or that direction, doesn't really matter. But only one possible path. There's no way it can go anywhere else. This is a switch, by the way, if you're wondering what that symbol is. Okay? So, one possible path. As a result of that, in red here it says the current is the same at all points of the circuit. So going back to our diagram, the current would be measured with these red A's, they're called ammeters, and they would have 3 amps there, 3 amps there, 3 amps there, etc. Whatever the value is, I'll show you the value in a minute, but the current reading in each of those spots would be the same. I'll show you how we'll determine what that value is in just a second. Okay? But since there's only one path, they all get the same amount. Now that may seem a little bit contradictory to what logic might say to you. Well, if the current comes out of here and then it has to work to get through this resistor, it slows down a little bit. And so it's measured a little lower here. And then it has to work to get through that resistor, so it slows down a little bit more. And then it gets measured here, and then it has to go through this resistor, and by the time it gets back to the battery, it's just limping along. And that's not the case. Every electron is already present in all of these devices, all of these resistors, all of these wires, and as soon as that switch closes, this little blue switch here, as soon as that closes, they all get the signal to move or drift, if this is a DC circuit, at the same time. Okay, so the recording in each one would be identical. Okay, next. Or let me give you an example, first of all, of a series circuit. An older strand of Christmas tree lights is an example of a series circuit, where if each of these resistors were replaced by light bulbs, and let's say you had 50 of them along your strand of Christmas tree lights, if one of those bulbs goes out, it's the same thing as just opening up this switch. The whole strand goes dark. And that happens if you have an older strand of Christmas tree lights, and many people do, because they, why get rid of them, So if one bulb goes out, you have to go through bulb by bulb with a replacement bulb to find out which bulb is the blown one. So it's kind of it can be good, but it's kind of a con, so to speak, of a series circuit. Another example, let me give you another analogy of a series circuit with only one path. If you were to go to a gas station and fill up your car with gas, which we're using a lot less of these days, traveling less, right? But if you were to go and grab that hose from the gas pump, that pump is like an ammeter, because it records every single drop of gas that goes from the owner's tank, gas station owner's tank below ground, has to go through that pump before it goes into your car. Okay, there's only one possible route for that gas to get to your car, and that is to go through that meter. Okay? Number 2, the total resistance of a series circuit is found by simply adding up all of the resistances that you have. So let me go back to our example. So I stated the problem had a 1 ohm, a 2 ohm, and a 3 ohm resistor. That's the omega symbol, if you're wondering what that is. So the RT in blue here is 1 ohm plus 2 ohm plus 3 ohms equals 6 ohms. Very straightforward. Okay? It's the simplest characteristic for a series circuit is the total resistance is just found by adding them up. Simple. The current total, characteristic number 3, this is Ohm's law. You hopefully recognize that. VT over RT, and the T stands for total. So we just apply Ohm's law. We know everything now because we just found the resistance. The voltage was given in the problem. So in green here, we have 18 volts divided by our 6 ohms of resistance. 18 divided by 6 is 3. So each of these meters would record 3 amps. And I stated that here, current at branch number 1 is 3 amps, or resistor number 1. Current at resistor number 2 is 3 amps, and current at resistor number 3 is 3 amps. The current's the same everywhere. That's what we would expect. Okay? So that's the current value. Number 4, this word voltage drop, you could use the different word. You could use voltage used, voltage consumed, voltage spent, voltage needed, voltage required. They all mean the same thing. But in electronics terminology, they use the word drop or dropped. So the N stands for whatever resistor you want to locate or find the voltage drop at. IN, it could be I1, I2, I3, etc. So if we find the voltage drop, it's just Ohm's law solving for V, if you recognize that. I times R, it's just this equation solving it for V. It's I1 times R1, it's 3 times 1 is 3 volts. V2 is I2 times R2, it's 3 times 2 ohms. Now we have 6 volts dropped. Now we have 1 volt dropped, 6 volts dropped. We've dropped 7 volts already out of our 18 volt battery. So at voltage at resistor number 3, we have 3 amps times 3 ohms. We have 9 volts dropped here. Okay? We have more volts dropped here because the resistance is higher. It takes more electrical pressure to get through here than it does any of the other ones because it's probably either a thinner wire or a longer wire in that resistor, which makes it more resistant, which makes it more voltage to get through it. So that's the voltage drop or voltage needed. And lastly, in our, going the wrong way, the last thing, it's not necessarily a characteristic, but it's more of a check for you. The total voltage in a series circuit is the sum of all of your voltage drops. It's a way for you to go back and check your work. Do my 3 voltage drops that I just did in number 4, do they add up to equal my 18 volt battery supply that was stated in the problem? So let's take a look. My VT, I have 3 volts at number 1, I have 6 volts at number 2, and I have 9 volts at number 3. 3 plus 6 plus 9 equals 18, and I had an 18 volt battery. So that's, if you didn't realize what we were doing, we looked at the 3 components of Ohm's law. We looked at resistance, we looked at current, and we looked at voltage. Those are the 3 things that make up Ohm's law. And we went through and we found or measured or calculated those 3 components at each of the parts of the circuit. And that's what you would do on a test question. Typically, you would be given a circuit and you would need to find the total resistance, you would need to find the total current, and you'd need to find the voltage drop at all points of the circuit, or the current at all parts of the circuit. And a series circuit is really pretty straightforward, so it's a good one to start with. Okay? So the second video, I'm going to walk you through that sample test question. So go through this again if you'd like, but have your page 3 of your notes, have that one ready to go.